So the what we have now is a system in the first midterm where we decided that we have three single particle states which are labeled by the standard atomic physics numbers. And this means that we have in each of these cases we have a slot here which can have a spin up, and this has a spin down. And similarly here we have a spin up and a spin down, a spin up and a spin down. And the total angular momentum L is equal to 0, so we don't need to bother that much about with that one. And the thing we have to pay attention to now is, like, if we're looking at the helium, in helium we would then have the 1s orbitals being filled, so that would be the ansatz for the Slater determinant. So we would then have a phi 0 of helium, so that would be the ansatz for that state. And then we have 6 slots here, so we would have 6 single particle slots. So that means that when you are setting up the matrix elements for the Hartree-Fock calculation, what you would need to think of then is to put some specific labels on the different single particle states. So that means that if you now think back to one of the really first homeworks which we had, you could now give a label 1 to this one. This could be state 2, this could be your state 3, and this would be state 4, and 5, and 6. So what you need to set up then, when you have made this table of single particle states, then you need to fill in the matrix elements. So that means that you would have a matrix element of the type P, Q, V of RS. And one of the matrix elements could be a matrix element of the type 1, 2. And you know that the anti-symmetrized matrix elements, when they are in the same single particle state, they have to be 0, right? So that means that you would have a matrix element of this type, anti-symmetrized. You would then also have matrix element of the type of either 1, 3 and 1, 4. So you could now fill in all the other single particle states of 1, 3, anti-symmetrized, etc. Now, there's one thing which you also need to keep in mind when you're setting up the calculation of the helium, is that the total spin has to be conserved. So when you sum up the spins of these states, there are some matrix elements which will vanish automatically. So if you look at the state which when you plug together 1 and 2, that has a total spin projection of +1. Whereas we are only interested in spin projections with values of 0. 1 and 2.
And 1 and 2 is 0.
Yeah. 3 and 4 is 0, 5 and 6.
Yeah.
But then 1 and 4 is 0, and 1 and 6 is 0. So you just need to pick out the right matrix elements. And the same thing will also apply when you have to be a little bit more careful when you're looking at beryllium, because there you're actually running over a total 4-particle state which has spin equal to 0. So when you're then running over the matrix element, just be a little bit careful with which matrix elements you're summing over. So the type of problems you need to look at then is the setup of these matrix elements. So you would then have a set of these, and you have the analytical expressions for the integrals. And that means that with the analytical expressions for the integrals, you can then proceed and then set up the full table over all these elements. And then simply in your Hartree-Fock program, you will simply look up in a table, you would send in the right indices, and then look up in the table. So if we go back to the code then, you would then see something like this. So in the code here, we have now assumed that you have made such a table. And when you've made such a table of single particle energies and the 2-body matrix elements, what we are starting with now is the first approximation, where we simply put these coefficient matrices, the matrix elements, to 1 along the diagonal. And this is a function of the number of single particle orbitals. So that would be all the orbitals. Because remember now that what we define as a density depends on the number of occupied states. But in our case, we have 6 single particle orbitals. 1s will spin up and down, 2s will spin up and down, and 3s will spin up and down. So in our case, the number of single particle orbitals is 6. And then we set up the density matrix, which is now a 6 by 6 matrix. And then here we are simply plugging in the values of 1. So we are simply calculating the density matrix in the first iteration, which is now outside the Hartree-Fock iteration itself. And here you would find something like max iterations. The first energy difference is equal to 1. So we are going to make an iterative process where we perform the Hartree-Fock calculation till we have reached this convergence criterion. Actually, it's convergence criteria. So if it's less than the number of iterations we put and the difference, then we just keep going. And here we set up the Hartree-Fock matrix. We run over alpha and beta. And here we set up the Fock matrix element. And you see now I have the density matrix. And this now picks up this interaction matrix element. And we simply need to have a table there where we have this tabulated. And we're not going to do anything fancy. We're not going to think of any type of symmetries which can be used to reduce the dimensionality of this table of matrix elements, because we don't have that many. So if you just think of you now having 6 single particle states, since you have on the Brown and Ketz side, it means that without thinking of symmetries, you can then have 6 to the power of 2 on the Brass side, so 2-body state, and 6 to the power of 2 on the Ketz side. So the dimensionality is 36 times 36. So it means that the table itself, without any kind of symmetry considerations, if we just list the whole the set of matrix elements, is going to be a matrix of 36 times 36. But you could make a table now where you simply have, you don't need to set up a matrix, but you can actually set up a 4-dimensional tensor. And that's the simplest possible way of doing this. And then when you do this now, you obviously have the one-body term, and we have assumed that the one-body piece is one which is defined by the single particle basis, so that everything is diagonal in that single particle basis. So alpha has to be equal to beta. And then we simply add this single particle piece as you see here. And then when you're done with that, we define a new density matrix. And then we simply calculate the new density matrix based on the eigenvectors which we get here. So we are diagonalizing the Hartree-Fock matrix. And then we get the new coefficients, which you see here. And these new coefficients are simply used to calculate the new density matrix. And then with the new density matrix, we can then proceed back again and then calculate a new Hartree-Fock matrix. And then we continue till the number of iterations stops. And here we have, we calculate the new energies, which are given by the results of the diagonalization, which follows from this quantity with this line, which we have up here. So this is just an eigenvalue solver, which returns the energies and the coefficients, which are actually the eigenvectors. And then we set up the old energies, and then we calculate this difference by simply taking the difference between the new and the old, as you can see here. New energies minus old energies, dividing by the total number of single particle electrons. That's just one way of testing whether we have reached a convergence. Okay, so, and that's essentially the kind of skeleton of a program which you could then take and use in setting up the Hartree-Fock solver. So the only thing you need to do now is to look at the matrix elements which you've been using in order to set up the one particle, one hole matrix to diagonalize. And that should contain the matrix elements which are relevant for the Hartree-Fock calculation. Any questions about that? So this is actually the very last part of the project. This is the last exercise.
It's incredible how big the dimensionality explodes. I didn't imagine it was this.
Yeah. So, and this is basically the problem with all this kind of wave function based methods, that the dimensionality explodes quickly. So in quantum chemistry, for instance, we are dealing just with a Coulomb interaction. depending on the basis states you have, you can actually have a basis set like Gaussian orbitals, where you can define recursion relations, and then you can calculate these matrix elements on the fly. And that's more efficient than making a monstrous table and then searching in that table or looking up in that table for the right matrix elements. So this is always this kind of trade-off. In the calculations I've been doing, we've typically had something close to 1,000 single particle states. And that means that the dimensionalities you get for the matrix elements can become pretty large. But for us, it takes so much time to calculate this table of matrix elements, the basic ones, starting with the ansatz for the basis you take. It could be a hydrogen-like basis, it could be a harmonic oscillator-like basis. But sometimes it takes so much time to recalculate these matrix elements that you simply tabulate them. But then you're limited by the amount of matrix elements which you have. And that's clearly a big problem, which limits you being able to go to larger dimensionalities in the number of single particle states. So just remember that we always truncate the number of single particle states. And what we have done in this midterm here is actually a truncation. So we have truncated this in terms of a free S single particle state, which is the last one. And we have skipped in atomic physics, if you spool back to what you did back in basic quantum physics, we have 2p orbitals, we have 3p, 3d, etc., etc. And we have skipped all of these single particle states. So we're just looking at the S waves, which normally dominate the contribution to the energy. Okay. So the thing which I wanted to switch over to now is actually to look at the stability of the Hartree-Fock equations. And we are going to run through something which is called Thouless theorem before we actually start looking at the stability of the equations. And what I'm going to do now is actually switch back to the whiteboard. So let's do that and hope that everything comes up properly. So the topic which we are going to cover now is about the stability of the Hartree-Fock equations. Of Hartree-Fock equations. And in order to do these studies, we actually need something which is called Thouless theorem. I don't know if I'm pronouncing this correctly or not. And the main findings. So we are going back to Thouless theorem, but what I want to do now is actually to start with some of the basic assumptions and state the results of Thouless theorem. And then we are going back to that one, because the point which is interesting for us is to study the stability of the Hartree-Fock equations. So we need the theorem, and then when we've gone through the analysis of the stability of the equations, we are going then to go back again and then derive the theorem. So the stability part is the most important one for us, because we can actually read off from the matrix elements which ones are those which may give us a stable solution for Hartree-Fock calculations. Okay, so what we are going to do now is, if we now look back at what we've been having, so we have this Slater determinant for the ground state of a given system, which we also label in terms of this quantity C for a core, for instance. And this is now given by the product of all the single particle states which fill up to the Fermi level. So we would have this creation operators acting on a true vacuum. So this is our Slater determinant, the representation of the Slater determinant. So this is an SD Slater determinant in second quantization. So what Thouless theorem says, and we are going back to the proof of that later, that says that we can actually define a new Slater determinant, C prime, which is similar to the one we have, but the Slater determinant can now be written out in terms of the following expression. Let me just find the right notes which I have here. This one's from. So what it says is that an arbitrary Slater determinant can be written out in the following way. And the way this Slater determinant can be written out now is in terms of the basic Slater determinant C, which we had before, plus a small variation. And we are going to write this small variation as a delta C here. So this is also Slater determinant, which we can write based on the vacuum state which we have defined. And this Slater determinant is going to be given by 1 plus, and it contains a sum over the one particle, one hole excitations, and we have a coefficient delta CIA, and this is then multiplied with the creation operator for a particle state above the Fermi level. So remember now that these indices A, B, C, and so on are states above the Fermi level, and the indices I, J, K, and L are for states below the Fermi level. And this is given by AI, and this is acting on the state C. So when we did the Hartree-Fock calculation, what we did was actually to vary the equations in terms of these coefficients, the CAI. So we are coming back to the derivation of the theorem a little bit later, but you can actually state a general Slater determinant in terms of the basis Slater determinant plus a sum over one particle, one hole excitations. And we are going to vary these coefficients C here. So what we want now is to prove that the state which we have, this C of H, is a local minimum. So that means we have also labeled this as an E0 Hartree-Fock. So we are assuming now that we have performed the Hartree-Fock calculation. And what we are going to study now is actually the calculation in terms of this new Slater determinant, which is not necessarily normalized. So then that means that we have to do a normalization, a proper normalization here. And we actually want this one to be larger or equal than the Hartree-Fock ground state, which we have found. So the stability criterion is now going to require that this general Slater determinant is a Slater determinant which gives us an energy which is either equal to the minimum which we have, the local minimum, or larger than the local minimum. So these type of equations are the equations which we're going to use now. And the way we are going to run through these calculations is now to look at the variational principle. So what we have now is this delta of C, which is now given by the sum over AI. And then we have a coefficients delta here of AI. And then we have A and AI here, acting on the vacuum state C. So we are now assuming that this vacuum state C here is now our Hartree-Fock vacuum state. Okay, so what we are going to do then is to vary the problem. So what we want to require now is that this expectation value here should be equal to 0. So we want to minimize that. So that means that what we want now, so this is just another way of stating the variational principle which we looked at earlier. You can do the emission conjugate, and since these two, the emission conjugate of the delta C parameters, they are result in independent equations. It suffices to look at the one where we have the delta C on the brass side of the equations. So what we need to look at now is actually an expectation value of the type AI, and then we have a delta, and then we have this coefficient CAI complex conjugate, and then we have C, and then this is multiplied with an A of I dagger, AA. So this is the emission conjugate of the state delta C. And this is then multiplied with the Hamiltonian and equal to 0. So this is the quantity which we want to drive to 0. And what we're going to do now is simply to run through the applications of Wick's theorem. We are plugging in the Hamiltonian, and then we look at the contractions. And based on that, we are going to derive a set of equations which would put constraints on the matrix elements of the interaction and their relation to the single particle energies. So I wanted to go through this first, and then we go back and we derive Thouless theorem. But now, let's suppose we have made such a perturbation. So you could motivate such a perturbation without thinking of Thouless theorem. So what you could think of now is that you're looking at a new Slater determinant, where what you're doing is that you add to this new Slater determinant a one particle, one hole excitation. So the way to read this quantity here is the original one, where you have filled all single particle states up to the Fermi level, and you simply add a perturbation to it. And that perturbation is given by the one particle, one hole excitations. So, and as you saw previously, we showed that Hartree-Fock theory is the same as putting the overlap between the ground state and the one particle, one hole excitations to 0. So 2 weeks ago, when we did the derivations of the Hartree-Fock theory, we actually showed that these matrix elements here have to be 0. And that's the condition for setting up the Hartree-Fock equations. And let's now look at the equations again and see if we can find some constraints on the single particle energies. So think of Thouless theorem as just a perturbation of the ground state ansatz we are making in terms of just one particle, one hole excitations. You can clearly add two particle to hole excitations if you want to. The only problem then is that you can then show that you cannot write a general Slater determinants in terms of the same type of operations which you have here, where you have redefined the excitation or the creation and annihilation operators. So there are some subtleties here which hinders us from including further correlations here, like the type 2 particle 2 hole. We are coming back to that in a connection with the derivation of Thouless theorem. So what I'm hoping for now is that you can accept that what we are doing here can be seen as just us adding a one particle, one hole excitation to the ansatz we made for the Slater determinant. And then we require that this overlap here is going to be 0. So we could have done this without thinking of the variational theorem, and we didn't need to put this equal to a delta C either. You could actually thinking of us searching for a way to find a unitary transformation which zeroes out these matrix elements. Period. Okay, so now we need to go through this boring exercise of calculating the matrix elements. So we remember now that H contains a one-body piece. So that contains a piece which runs like PQ. And then I have the matrix elements P of H0 of Q. And then we have this normalized matrix elements with respect to a new vacuum. We are skipping that way to nominate, to define them. And in principle, what we have then is additional matrix elements, and we could rewrite this in terms of the new vacuum state, but let's just leave it as it stands now. And then we have a PQ RS, and then we have the matrix elements of the P, of Q, of V, and RS, and then we have the operators AP, so these are anti-symmetrized matrix elements, AQ, dagger, AS, AR. So the thing we need to look at now are just the various contractions. So we need to look at the contractions between this one and these operators here. And we need the same one in connection with these operators here. But we have also to be a little bit careful because the sums we are looking, the calculations we need to perform contain also a denominator here, because we haven't normalized these matrix elements. So that means that we need, if we follow the standard rules of quantum mechanics, we need actually to divide by the normalization term. So that means that there is a small term which we need also to pay attention to. But let's take now a look at the different calculations for the denominator, not the numerator, which we need to look at. So what we need to take into account is just a sum. So I'm just setting these up in a more schematic way, and I'm just going to look at the operators. So I'm not going to include the matrix elements themselves. So I hope you can forgive me there. So what we need now is simply to set up C, and then we have the AI, AA, and we do actually have a sum over A and I here, so we have to keep that in mind. And then we have an AP and an AQ here. Let's see. So that's one of the terms which we need to look at. And in this particular case, we know that when we look at the contractions, obviously this one to that one is 0. This one to this one is 0. We know that this one to this one is 0 by definition. This one to that one cannot be done because this is a normalized string of operators, because if we do this one, we will also have to do that one, which is 0 by definition. And you see that the only contractions which survive are this one and that one. So what we get from that specific term, so this gives us simply this contraction, which is non-zero, and these are the only non-zero contractions. So what we have then is a delta AP and a delta IQ. That's the first piece. The next piece we need to look at is the two-body interaction. And then we have more terms which we need to pay attention to. So let's take a closer look at the two-body interaction. So we will now have a sum over A and I, and we have a sum over P and Q, and R and S. And I'm leaving out the matrix elements and all these factors. I'm just looking at the sums here. And now we have a C, and then we have an A of I dagger AA, and then we have an AP dagger, AQ dagger, AS, and AR of C. And as I said, I'm leaving out all the specific matrix elements because we're just going to look at the contractions which take place here. And what I thought we could do now is just, since we are a little bit over time, we can take a small break and just stretch legs and then come back in roughly 10-15 minutes. So I'm just going to put a recording on break. So what we need to do now is first to calculate these contractions, and after we've done with that, we are going to calculate this expectation value. Now, by looking at the equations which we have, there was one thing which I forgot to mention, because now we are using the normal ordered Hamiltonian with respect to vacuum state. And in here, it's not H0, but it's actually this operator F, which we defined in connection with Hartree-Fock theory when we defined a normal ordered Hamiltonian. And that means that this piece F contains the standard single particle operator H0 plus the so-called mean field, which is set up by all the occupied states. So this first piece has only one set of truncations, which or contractions, which are non-zero. Now, if you look at the next term, we can almost, without having done any calculations, we can just read off that this has to be equal to 0. And the reason for that is that we are actually having two chains of normal ordered operators. So we cannot, when we use Wick's generalized theorem, we cannot take contractions within the same operator. And you see now that when we do some contractions here, we could have this one, and then we could have this, but then we have an uncontracted set of operators here, and that is equal to 0. And by looking at all the possible combinations, you will see that the second term actually gives us 0. So this term here is something which ends up by being 0. And the only term which survives now is the term here, where we have reduced P and Q to be equal to A and I. So what we have then is a term which runs like, so this means that what we have are these coefficients C delta C AI. So we're going to have a sum over AI. And then we have the matrix elements between I. And then we have this operator F. And then we have A. So now we're just plugging in the terms here. And we are simply requiring that this piece here has to be equal to 0 for each pair of AI. And if we now look back at the expressions for F, so let's quickly remind ourselves of the expression for F. This is given by the single particle operator. And we have this term here, plus, and then we have a term which runs over all the states below the Fermi level. And then we have an IJ, V, and then we have finally an AJ, and this is an anti-symmetrized matrix. And this is the so-called modified one-body operator with respect to the new vacuum. And it's also an operator which gives us the matrix elements, which we call the Hartree-Fock matrix elements. So from a diagrammatic point of view, if we want to replace everything in terms of diagrams, these matrix elements would then be rewritten in terms of a matrix element like this, where we now have a one-body operator here, which is H0, and then we have an incoming particle state A and an outgoing whole state I. So this is a way to write that specific matrix element. And, oh, by the way, I think I did interchange here, sorry. So I made a small, because we have the contractions of the AI here, and we looked at the brass side with the coefficients, whereas in the previous case we had the ket side. So this actually gives the opposite, because we have an AP. So remember that the matrix elements we are looking at are F of Q here. So it's actually, I did the opposite shot. Right? We have to change this one and that one, and this one as well, and this one as well. So let's just do it correctly, because I forgot that we actually are doing this. So we have A here and I here. So it's an A and an I. And that means that we have A here and I here. And that means that the matrix element is going to look like this in a diagrammatic representation. So we have A leaving and I coming in. And then we have the second term, which is something which we wrote. If we now write it out in terms of the exchange and the direct term, we would have now the single whole states which comes in, this particle state which leaves, and then we have the sum over the states below the Fermi level. So this would be a J here. And then we have the next term, which looks like this. So we could have an A leaving, an A leaving here, an I coming in. And then we have this whole state J here, which we label like this. And then we have this one. Alternatively, these two last terms, they could now be shrinked into just a so-called Hoogenholz diagram, and where we just have a loop here, J here. So that's a typical representation of an antisymmetric diagram. So where we have connected, where we have lumped together both the direct term and the exchange term.
Was the A leaving or it's
The A is leaving
Yeah.
actually. The A is leaving and the I is coming in.
Yeah.
Because you see the matrix elements here, we have the I coming in, I comes in, and A is just leaving.
Yeah.
So this would be the diagrammatic representation. And if you think of the midterm, this is exactly one of the exercises you were being asked about. And we discussed this, I think it was 3 weeks ago. Now, what we are going to look at now is the calculation of the stability of the Hartree-Fock equation. So what we need to, when we are looking at the stability of the equations, so in a sense, what we did now was simply to say that my Slater determinant, if I now add to the ground state ansatz, just have one particle, one hole excitation, and if I vary that one and require that that one is 0, that specific expectation value, then I end up with the standard Hartree-Fock equations. But let's now assume that we keep this and we look at the stability of the Hartree-Fock equation by calculating this specific matrix elements here. And now, since this C prime is not normalized, we need to divide with a normalization factor. And what we want to is that this one is larger or equal to the calculation we will now run with a Slater determinant, which by some assumption is assumed now to give us a local minimum. And again, we can actually rewrite this Slater determinant in terms of the same expression as we did before. But now we have to be a little bit careful in the sense that the Slater determinants here will now contain the creation and annihilation operators for the one particle, one hole states. We would have one which comes from this part and one which comes from this part. And then we will also have a similar term here. And we have, in a sense, what we've done, and this is Thouless theorem, states that there is a Slater determinant, a general one, which we can actually write like this. But where we can actually show that we can rewrite it in terms of just a one particle, one hole excitation. So this is going to contain something like a delta C AI of AA of AI. And this is acting on the vacuum state. This is what we're going to prove a little bit later. If we now look at the denominator, we are now going to truncate this denominator at a term which goes like delta C squared. So we will now rewrite this one. If we now take so it's the principle is just a truncation. So we would get that one as a sum over AI. And then we are going to have a delta C AI squared. And then we leave out high order terms. So we have also assumed that this C of C prime is different from 1, but it's non-zero. Then we can also use what we introduced a little bit earlier, which we call intermediate normalization. So you can always redefine the way you normalize something, and then we can just use this property here, that this is equal to 1. So if we now calculate the expectation values here, what we need to evaluate when we calculate the term here is now a term. So if we write it down, we're going to get a C of H C. That will be the first term. And then we have the next term is now going to have a sum over AI, and it's going to have a sum over BJ, because we are actually squaring these matrix elements. And then we are going to get now a term which goes like delta C of AI complex conjugate. We are going to have a term, and remember now that I'm not putting in the terms which contain only one delta, because with the Hartree-Fock approximation, we have actually showed that that term, as we've done here, is equal to 0. So that means that when we write this out now, the only terms which survive are those where we have the coefficient squared, because with the Hartree-Fock calculation we have done, then we have showed that the expectation values. So let me just quickly remind you. So we did actually require that these terms are equal to 0. So that means that when you now multiply things here, you would obviously have one term which goes like C, and then I would have H, and then delta C, and I would have the similar thing from the brass side. And these terms are by definition 0 now, because we have assumed that we have optimized the terms. Okay, so that's why I only have the terms which now are going to run as a function of delta C squared. So that means that I will have a delta C of Bj, and then I'm going to have to multiply that one with C, and then I have my I dagger, AA, I have H, and then I have my AB, AJ of C, like this. And now I have to be a little bit careful. So what I'm going to do now is to make a truncation of the series expansion, which you see here. I'm going to truncate that one to second order, because I want to keep terms which now contain, if we now look at this term which you see here, so it's going to have a 1 plus an AI, and then I'm going to have this delta AI of A of AI, like this, and then I'm going to have the terms squared. And when I do the Taylor expansion of this quantity, there's going to be a 1/2. And then I'm going to have a sum over AI, a sum over Bj. And this is going to contain a delta C of AI, a delta of C of Bj. And then I'm going to have the creation and annihilation operators. So when I now, since I'm now keeping terms only to second order, I have to be a little bit careful with the way I make the expansion of C prime. Because then there will be a term which goes like C squared here, multiplied with just C. And then there will be a term here with C squared, which is just multiplied with C from that side. So I have to be a little bit careful where I truncate my series. So Thouless theorem states that we can write a general Slater determinant in this way here. We are going to make a expansion, and when we calculated the Hartree-Fock equations, we simply stopped here. But now we have to be a little bit careful when we are calculating this expectation value, because if I stop at second order, if I stop at first order in delta C, then I just have the Hartree-Fock equations. If I now stop at second order, I get one term like this, but then I need further terms, and there will be a term here which is going to contain the interaction in a similar way as before with the Hamiltonian. So we're going to get a factor of 1/2 from the Taylor expansion. So we're going to have an AI and then a sum over Bj. And in the first term, we're going to have not the complex conjugate, but we're going to have a C of I and a C of Bj, like this. And this contains now the matrix element of C, and then I have the Hamiltonian of H, like this. And then I'm going to have an A dagger, AI, a B dagger, AJ, acting on C. And since I'm truncating at second order in the parameters delta C, I'm going to get a new term here. And that 1/2 comes from the Taylor expansion of the Slater determinants given by Thouless theorem. And I'm going to have the next term here, which is going to contain the same type of sum, AI, Bj, and then I'm going to have a delta CAI, but now this is complex conjugate because it comes from the brass side. And then I have a delta of C of Bj, complex conjugate. And now I have a matrix element which looks like this. So I have a C, and then I have an A, and now I have to be a little bit careful because this is going to be AJ, going to have AB, it's going to have AA, and sorry, AI, and AB, AA, and this acts with on the Hamiltonian C here. Now we have to go through the calculation of all these matrix elements in order to try to reduce the calculation to something simpler. So we have to use Wick's theorem now, repeated for unrepeated matrix elements, and just see what we get. So what I did, just to remind you of that, I have a general Slater determinant, EX, which is now written as a sum of particle hole excitations. So I have this delta C of AI and AA acting on the vacuum state. And this is something we could rewrite in terms of C plus, and then I have a sum over AI of delta CAI, and then AA dagger AI acting on C. And then the next term would be 1/2. And then I have this term squared, AI of delta CAI of AI. This is squared. And this is then multiplied with C. So this is a truncation which we made. And the reason why I stop at second order here is that when we look at the matrix elements here, for this specific term here, I'm obviously going to get a term which is C times H times C. And then I get a term which goes like C times H. And then I have this delta C, right? And plus a new term which goes like delta C of H of C. And then I have the three higher order terms. So I would then get a term which goes like delta C of H, delta C, and then I have plus, and then I have C of H of delta C squared, plus delta C squared of H multiplied with C. So I made this truncation to second order in the Taylor expansion of the generalized Slater determinants which come from Thouless theorem. So with that, what we end up with is a set of equations which some of them we know the answers. So in the Hartree-Fock calculation, this is equal to 0, and this is equal to 0. So we only left with the standard term which we had before, which is the vacuum expectation value. And then we have 3 additional terms. And these are the terms now which we need to look a little bit more carefully at. Yeah.
Isn't there another term as well? The delta C squared H delta C squared?
No, because we stopped at the delta C to the power of 2.
Oh.
So you would have a term which goes like delta C squared, but we stop everything at the level of delta C squared. So we make a truncation now where we also truncate the denominator here in this expression. We truncate that one also at the level of delta C squared, so that we are consistent with the truncations in the numerator and the denominator. Yeah, that will clearly give us an additional term. And but then we wouldn't have a symmetry between the denominator and the numerator. So we want to have a symmetry between these two in terms of the unknown coefficients delta C. And by the Hartree-Fock equations, the terms which include C and delta C, they are exactly equal to 0 by definition. So when we now run through the contractions, if we now look at the first term, which we need to look at, so we will have something like this, C of A dagger, AI. So if we go back to the equations which we have, so we're now having a term like this one, the one here. So let's take a closer look at that one. So we have a term which runs like that. So we would have an A of B. Actually, this is not, it's an A of I. I have to look, sorry. So this is an I. This is an AB and an AJ for the vacuum state. Okay, so let's now do the one body piece and the two body piece. So the only thing I'm going to do now is just set up the operators, and we leave out the matrix elements because else we get too many terms in the equations. So if we look at this term here, what we're going to have now is just contractions between strings of operators of the type AA, and then we have an AP, so that's the one body piece, an AQ, and then we have an AB of AJ of C. So here we can make the following contractions, which are non-zero. And you see now that we can contract this one with that. And that means also that we can contract this one with that. And then clearly the only option here now is that we have a delta IJ. So this gives us a delta IJ. And then we have a delta AP multiplied with a delta A, delta Q of B. So that will give us a matrix element. When we look at that one, that will give us a matrix element where we have A of F, and then we have a B here, and this is multiplied with a delta IJ. So if we want to write this, so this would be the, these are actually if now, B and A, if that is an eigenbasis of F, then clearly this just reduces to what we would call the Hartree-Fock energies. And by definition, the new basis A and B is going to be the Hartree-Fock basis. So that means that these guys here are going to be diagonal in A and B if we have a Hartree-Fock basis. Because F defines also the Hartree-Fock operator. So this specific matrix element is something we can replace with a single particle energies epsilon of A Hartree-Fock. So this could equally easily become epsilon A Hartree-Fock of delta A B and delta IJ. But in general, if we are writing this in a diagrammatic way, what we would get then is something like this. So we would have the operator here, F. So this is F here, and we have the state B coming in and the state A leaving. And then we have a bystanding whole state, which doesn't do anything, and which we write simply like an I here. So that would be the diagrammatic representation of that specific term. Now we have a further contraction here. So if we just bring up the same equation again. So we have an A of I of AA, and then we have an AP dagger, and we have an AQ, and then we have an AB dagger of an AJ of C. If we now look at this one, what we have as a further contraction here is a term which goes like this one. That's a contraction which is fully viable. And then we have P going to J. Now we have a crossing fermion line here, and that's going to give rise to a factor of -1. And then we have the contractions between A and D. This is also non-zero. So that's going to give us a term which now leads to minus, and I get a j of f of I, and this is multiplied with delta A and B.
But don't we have two crossing lines in this case?
No, because when what I can do now, I can always interchange the creation and annihilation operators. If you look at that, so with A and AI can be interchanged, but with a minus sign, and these two here can be interchanged. So J comes there, and then when I take the contractions, I have still a crossing line. So you have to think about, because the B is different from J by definition. So that means that this contraction here, I can always swap them. So that gives me a minus sign. And I do the same with these, that gives you a minus sign. But what I would be left with then is now AI dagger, AP dagger, AB, and then AJ. And then the contraction which I'm looking at is actually this contraction. No, not AB, but AQ here. So it's this contraction and then this contraction. And there I get a minus sign. And this is something which translates into a whole line. And this is a whole line which goes through the whole diagram, and that gives a rise to factor minus. So the diagrammatic representation of that would be particle state A here, which doesn't interact with anything. And then we would have the whole states. So I would have an I coming in like this, and then a J leaving. And then I have the interaction matrix element here, or the operator. So that would be the diagram. When you look at diagrams, you never put in signs in front of them, but you extract the sign by looking at the number of whole lines and number of loops as well. Okay, so that was this piece. Now we need to look at the next piece here. And since we now have this chain of operators, what we would get in addition now is the following. So we need to put in the two-body operator. So we have a C, and then we have an A, I dagger, AA, and now we have an AP dagger, AQ dagger, AS, and AR, and then I have an AB dagger and an AG, J there, multiplied with C there. So if you look at this term, now we have to be a little bit careful. So we have the contractions of the type which you see like this one. So that's a fully possible contraction. And then if we take the other particle line, this can contract with this one, or it can contract with that. And similarly, these two here can actually contract with B. Those are the only contractions for these operators if we want to link them to the particle states. But what you see now is that I cannot link AI with Q, which is now left alone. I can link I cannot link. I could link AI with this one. That's fully possible. But that would leave me with a contraction where I would have to take this one and that one. So that's fully possible. So let's take a look at the contractions which we could get here. And let's take this one away. And we'll try to look at all the possible contractions which we end up with. So we could now assume that we take this one like that. What we would need to do then is that we have this one now going to that. That's a possible contraction. And then we would have to link this one to this one. And you see now that now we have actually linked all the operators with some of the states here. So that's one possible set of contractions. And then we can what we can do next now, instead of having A here going to P, we can let A go to Q. Similarly, we can let B go to S. And then we can let AI, instead of AI going to S as we did here, we can let it go to R. And in total here, there will be 4 possible ways of setting up these type of contractions. So this is just one of the contractions which gives us a non-zero result. So if we look at the type of matrix element we would get when we are setting up all these types of contractions here, what you would get now is first we will get a delta. Okay, we will get a delta AP. That's one type of contractions we get. We get a delta of RB. Now we have to be a little bit careful because we need to swap operators. So we have to be getting, when we take AI with S, delta AIS, we actually need to swap AI with AQ. So that's going to give rise to a minus sign here. So we're getting a minus, and then we have a delta, the final one, which is delta of Q and J. So this is going to give us a matrix element, which looks like minus. So we have an A here, and we have I, and we have a V, and then we have a, no, sorry, we have an A. Okay, let me rewrite. So we have A and Q, so it's J here. And then we have R, which is equal to B, and S, which is equal to I. So this is an anti-symmetrized matrix element, and it has a factor of 1/4. Now, if you now look at these contractions here, there will be 3 more such contractions, which we are going to get. And they will all be of this kind of type of matrix elements here. And when we then use the symmetry of the matrix elements, we can actually rewrite them in terms of 4 equal matrix elements. And that's going to take away the factor of 1/4 here. So when we collect all these terms there, we are going to get an expression which is simpler. So we are going to get in total, for these type of contractions, there will be 4 more, no, 3 more total, 3 more of the same type. We will then get a matrix element which is simply given by minus AJ of V, B of I, anti-symmetrized. So what we got from this term, so with the C and the C times H, and then, sorry, C plus, I have to bring it back here. So this is delta C, delta C. When we put everything up here, we are going to have a sum over AI, J. It's going to be a minus. And this is going to contain now these different terms where we have the single particle pieces. So we're going to have an A of H of this F of B times delta IJ minus, and then we have J of F of I delta AB. So one of the sums here is going to be redundant. And then we're going to have minus, and then we have A of J, V of B of I, anti-symmetrized. And this is then multiplied with these coefficients which we have. So we have a delta C of AI, complex conjugate, multiplied with a delta C Bj. Okay, so now we're done with that specific term. And what we're going to do next now is simply to look at the other types of contractions which we have and see at the end what we end up with when we performed all the types of contractions here. So let's now look at the next term, And I have to reshuffle a little bit my notes here. So I have everything ready because there are many types of contractions which we have to look at, and it's easy to get lost here in the sea of contractions. So if we go back now, one of the other contractions which we have to look at is this. So we actually did this one, and now we have to take this one, and then later we have to take that. So let's do the next one. If we look at that one, what we end up with is a term which is going to contain these terms here, that one, and then we're going to have something which contains this piece here and this piece here. So let's look at the two additional terms which we have. So if we take now the term which goes like C of H of delta C squared, this is going to be proportional to, and what we are going to have then is C, and then we have the Hamiltonian H, and then we are going to have A of A, A of I, A of B diagonal, and A of J acting on C. And now we can redo the same exercise with the one-body operator and the two-body operator. And then we can do the same thing with the addition conjugate of that other quantity. So if we do that, now let's do the one here, and then we stop there. And then tomorrow we're just going to wrap it up in the first lecture, and then put everything together. And from that, we can say something about the stability of the Hartree-Fock equations. So you will also find the final equations in the slides here, in the weekly slides. But if we now run through that one, if we now look at the one-body term, so we are going to have a term which goes like C, and then we're going to have an operator, AP dagger, AQ, and then we have an A, and then an AI, an AB, and then an AJ here, like this. Now, in this specific case, we know that a contraction like this is possible. So that would be a Q of A. We cannot have a P to A. We cannot have P to B. So we could also have Q to B. But now you see that there's something going wrong here. So if I'm now trying to link the state, so this would be a possible contraction. Then what I'm left with is this one, and B and J are different. So this term here is actually going to give us 0. And you can see that by looking at the different contractions. So the only one which doesn't give us something which is 0 is the one which involves the two-body operator. So that means that the term here, which goes like AP dagger, AQ, AS, AR, multiplied with AA dagger, AI, and AB dagger, and AJ. This is the only non-zero term here. And then when we run the contractions here, we are going to get matrix elements. And so let's look at some of the type of matrix elements which we can get. So if you now look more carefully at what we will have now is R to A. That's a possible contraction. We would also have the S to B here. That means that we need to have Q going to I and P going to J. So that is a possible contraction, which is non-zero. And what we're going to see now, when we look at the matrix elements here, so this means that in terms of matrix elements, so P is equal to J, so we're going to get that one. The Q is equal to I, and then we have V here, and in this case, R is equal to A, and S is equal to B here, anti-symmetrized. Now, in this specific case, we also have a crossing fermion line, so that gives rise to a minus. And we can always rewrite that one as a plus of IJ of V and AB, anti-symmetrized. Now, due to the permutations which we can have here, there are 3 more matrix elements, so this is multiplied with a factor of 1/4. There are actually 3 more matrix elements which are going to give us the same type of expressions. And that means that we, in total, we are going to get something which is given by IJ V of AB, anti-symmetrized. When I take the other matrix element, the other one which has a delta C squared, then I'm going to get the Hermitian conjugate of that matrix element. So that means that the final term which we had, that means the term which is the Hermitian conjugate of that one, that will simply give us the Hermitian conjugate of that matrix element. So when I take the delta C squared of H of C here, what I'm going to get then is AB of V. Let's put that one, and then on the IJ here, anti-symmetrized. So I invite you to take a look at this kind of exercise. It's perhaps not the most exciting one, but what I wanted now to conclude is actually to go back to the slides and see how we can collect everything. And then tomorrow we are in the first lecture just going to discuss the Thouless theorem. But when we now grind ourselves through all these calculations, as you can see here, it's just a repeat of what we did on the whiteboard, we are going to get all these different contractions, and we can rewrite this in terms of coefficients which go like delta Ci squared. So this is just the vacuum expectation value which we have. And then we have a delta Ci, we have the single particle energies minus each other. And we have a sum over A and I, because we made the assumption that A is equal to B and I is equal to J, so we get rid of one of the double sums. And then we have the coefficients here. We have this AJ, V, and B of I. That was a term which contains delta C on the Ket side and the brass side. So this gives us these terms here. And then when we collect everything, we can rewrite these calculations in terms of a set of matrix elements where we now have the Hartree-Fock energies here, as you can see. And then we have the collected terms with delta C of I multiplied with this term. We have these matrix elements here, which actually AJ B of I, the one with a minus sign, which we have. And then we had the other ones with a plus sign, which now enter the definition of the matrix elements B here. So we have the B Hermitian conjugate, and then we have the other matrix element here. And then we have the unknown coefficients. And you can rewrite this when we now sort it out. We can rewrite it like that. And we have high order terms, which we in a way have neglected. So this delta E is the quantity which we now want to study in terms of these different matrix elements. So we can actually rewrite everything in terms of a more compact notation, where we end up with a matrix M here, where this matrix M is now given by, it has specific yields matrix elements delta E, where we have the coefficient vector. And then we have these matrix elements where we have the single particle energies along the diagonal. And then we have these matrix elements here. And this matrix here, in order for that one to fulfill the Hartree-Fock condition, this delta E should be larger or equal to 0 for the stability of the equations. Now, an important aspect then is that when we diagonalize this matrix, is that that should then be positive definite or semi-positive definite. And from that, you can read off a condition on the single particle states plus the diagonal matrix elements. There is a necessary but not sufficient relation in order for the matrix to be semi-positive definite. And that is that when you look at the sum over the diagonal elements, they should actually be larger or equal to 0. So that's a necessary but not sufficient condition. for the matrix to be semi-positive definite. So that means that you can actually go in and read the sum of these matrix elements and see whether that is larger or equal than 0. So that is an indication already of you being able to say something about the stability conditions. And I'm going to stop the recording now.